So having discussed the advantages and disadvantages of FEM, so we'll be moving on to the FEM, but especially applicable to the structures, which is solid mechanics types of problems. So here I have listed down the steps of finite element analysis, of your typical finite element analysis. So first, the step would be the decision of the what types of analysis is being suited to the problem. So whenever your user is given a problem, he needs to have a very clear understanding what types of analysis he should run in order to meet the requirements. Suppose there is a simple structure like in a beam, or if the user is analyzing some part within the aircraft which is being static and which is being bolted onto some other structure, a simple static analysis of the structure would do. And sometimes if the user is analyzing a wing component, there might be a dynamic loads, so there will be a dynamic analysis required, or if he wants to extract the natural frequencies, then he has to run the modal analysis. And sometimes the user might be interested in running the buckling analysis of the wing skins or the fuselage skins. And finally, the contact problems is a special type of nonlinear problem. And then similarly, thermal analysis problems. But for the structural analysis problems, first we need to, once the decision has been made that the structure is going to be analyzed for so and so analysis, the element types will be selected. So there are 2D and 3D element types, and obviously 1D elements 1D elements are nothing but your bar, beam and rod. Within 2D and 3D we have linear and quadratic elements. Linear in the sense the elements which have corner nodes, and quadratic is the ones which has mid-side nodes, middle nodes on the edges. It will have a middle nodes which is the higher order elements. And then finally, once the element have been selected, and you have to have the clear understanding of the material properties, what kind of properties you are going to give and what kind of values you are going to assign to each property variable. And then finally meshing, and then applying the loads and boundary conditions, and then solving the problem, and then extraction of the results. And always the finite element analysis should be accompanied by your simplified classical hand calculation, just to prove that whatever you have done using FEM makes sense, that it coincides with the simple calculation whatever you do, and the results are very similar and correlates with each other. That is just for the understanding of the user, that is just for the understanding of the engineer, to make sure that the analysis whatever he have done, whatever the assumptions he has considered within the analysis is correct. So there are some common types of elements that are used. So as I mentioned a few seconds back, there are 1D elements which are rods, beams, trusses and frames. Rod elements react only the axial loads. Beams react both axial bending loads, and then basically it can carry both axial and moments. Axial loads and moments. And then 2D elements. 2D we have plate and shells. Plate and shells is a type of uh, behavior based on the naming based on the behavior, but it is like trion and quad elements. triangular element and quadrilateral element is called quartz. Uh, Sometimes it is called plates. Why? Because it same similar to beam. It can resist axial and bending loads. Sometimes shells come in different forms. Sometimes shells can react only the in plane loads. They can't take any out of plane loads. Similarly, 3D elements. 3D might be a tet, and then yeah, prism block or hex element, brick element. So they can these 3D elements, and each element will have uh, element will have a set of degrees of freedom based on the degree of freedom of its nodes. These 3D elements don't have any rotational degrees of freedom. It has only the translational degrees of freedom. So in terms of finite element model validation, so what types of errors can occur? I have listed down just to have a feel what kind of mistakes can be done by users, and the impact can be huge. So first and foremost is the a structure or a domain that is being approximated using the finite element structure. What happens over here is like whenever um, there is a deformation of the structure which is very complex, it may not be accurately captured by the mathematical model. Suppose the user has used linear element, and the deflection might be pretty straight. It doesn't bend or it doesn't curve. So one has to be really careful in the selection of elements for a particular type of structure, and to be structure specific and to be analysis specific, just to make sure that they capture the behavior very closely. So in if the user selects cubic element, you can see that the deflection behavior or the deformation behavior is being very captured accurately. So I have put in this one just to make sure that the finite element user should keep in mind to select proper elements for their analysis, rather than going with some simpler elements, and then they end of the day they can't achieve the results what they want. And then finally, there are some integration techniques such as Gauss quadrature or something at the Gauss points. We call it as Gauss points, which is nothing but you have a quadrilateral element. Once the structure is solved, once the finite element model is run, and while you are extracting the results, what happens is the software computes the computes the unknown quantities such as displacements and loads in the nodal points. So first it computes for the element, and then finally it interpolates to the nodal points. So when it computes for the element, it uses a type of Gauss quadrature kind of techniques for computation. Sometimes what happens is during the post processing of the finite element, post processing is, as I mentioned earlier, when we extract the results, post processing, the averaging, there will be options for using the averaging, elemental averaging or nodal averaging, that can make a very huge difference. So one has to really keep in mind about these things. So I'll be speaking to you on these things in detail later in the course when we go into the pattern and astron, but just to give you an idea, so where the users may commit the errors. And also one other thing on the elemental selection is, higher the element order, higher your higher the degree of your the polynomial equation, so that it accurately captures all the behavior out of plane, in plane, rotations, etc. And few other mistakes done by the users are nothing but this one has been already discussed, which is the wrong selection of the elements. And then few other things are the distorted elements. While meshing, they don't mesh really properly, and the boundary of the structure is not captured accurately. If you see, there is a gap between the boundary and gap between the, it's not accurately captured. So these type of things, and the elements are completely skewed, completely distorted. And the next one will be the rigid body motions. Suppose the user forgets to apply any boundary condition. Suppose a cantilever beam you take, and one has to be the, sorry, simply supported beam, and the one end has to be hinged and other has to be fixed. So if both is hinged or if both is rolled, then what happens is, like, there will be a rigid body motion when you apply the axial force, it rolls down. So there is no proper boundary condition, and then there might be an inconsistent units, especially in the material properties. While creating the material properties, user might, finite element engineers might commit errors. So there might be a inconsistency in units. And then finally, large stiffness differences. Sorry, this might be the result of not having the proper assumption, not having how to idealize the real structure into the mathematical model. This falls into the idealization error. So later on we will discuss about these things much in detail. So moving forward, the same thing whatever I have spoken earlier. In terms of convergence, you have the number of elements, which is increasing the number of elements. I have put on a simple example. You can see a plate with a hole, which is being discretized using 228 triangular elements, tria element, 2D element, and then we done the H refinement to see it is with 912 elements, and this will provide, the more the number of elements, this will provide much more accurate solution in terms of the stress distribution around the hole, around the cutout, than this the coarse model. This is a very coarse rough model, and this is a very fine model. So this is what I have been speaking to you earlier, to for the to make the users of the finite element analysis to keep in mind there are certain things that could go wrong based on the assumptions. So now we'll be I'll be speaking to you on the finite element applications into the aircraft structures. So how to idealize the aircraft structures into the mathematical model, and how this is being done in the real-time scenario. So first, before going into that, I'd like to tell that the job of the finite element analysis within an aircraft industry might be right from sometimes creating the geometry, or sometimes you don't get a chance to create the geometry. Sometimes the design team within the uh, industry, they create the geometry and they give you the geometry, and then finally you make your own assumptions to create the mathematical model. The assumptions are what kind of boundary conditions to use, what kind of elements to use, how you can idealize the structure, very effectively, and then what kind of materials to use, and what kind of loads act on the structure, that should be accurately captured, or at least reasonably close sense. In a reasonably close sense, it should be captured onto the model. And then finally you should assign the failure criteria. Suppose if it is a composite model, you may be required to assign the failure criteria, Soy Hill or Soy Who criterion, and those kind of failure criteria and the parameters for the failure criteria and material strengths before you run the analysis, because different industries use different failure criteria for their material to be qualified. And again, the steps, what kind of steps you should take in order to achieve the result. So I have broken down these steps, and I have done what kind of steps you need. A typical problem may have some numbers, geometry, material properties, and the relational equations, which is the force displacement, equilibrium, and kinematic equations, strain displacement, and the stiffness equations, Hooke's law, and different types of material property equations. So one should be very much aware of these things, and one should have the sound subject knowledge. So this is what we have to use, and this is what we are going with, and proper justification of the of your actions. So this is what I have been using on the model, and this would give the proper closer result. And then finally we will be discussing the applicability of the FEA into on an aircraft. So looking at the aircraft component,